I'm going to talk about organic molecules on the moon with a focus really on some of the potential reactions mediated by lunar regolith. So to begin, I would like to say that this project is very much an outgrowth of studies of lunar regolith chemical reactivity from a biological standpoint, from the standpoint of trying to understand the toxicity of lunar dust. And we've been very gratified to discover that many of the concepts that we learned about in these fundamental studies of lunar dust, primarily Earth-based laboratory experiments, really apply to a very different sort of astrochemistry focus of lunar regolith as well. So it's been a very exciting discovery. So I won't belabor the point, except to say that there is evidence for organic molecules on the moon. I think that's something that most of the people in this audience would agree with. Some of that evidence, of course, comes from recent data obtained by Chandrayaan-1 orbiter, which obtained a lot of interesting spectral data. And there's been quite a bit of interesting data from the L-CROSS and LRO missions as well. So with that as a starting point, as a premise for my talk, what I'd really like to focus on is thinking about what would happen to some of these organic molecules as they interact with lunar regolith. It's worthwhile to consider what some of these sources of organic molecules on the moon would be. Certainly, one can think about meteorite impacts as potentially delivering a bulk of this material, along with water potentially and other molecules of interest. And it's also possible that interstellar dust, which may be delivered to the lunar surface as well, may contribute. So if you think about the moon as is today, there's certainly no human presence on the moon. But if we can look into the future, I think one might imagine that, in fact, in the near future, at least robotic missions to the moon may in fact contribute to some of the organic molecules on the moon. So here at Ames Research Center, we have a very nice mission design center. Unfortunately, I wasn't able to take advantage of their services, so I designed a mission of my own, and it looks like this. So what you see is a spacecraft, a very inexpensive one, oops-a-daisy, little bumpy ride there, landing on the moon, and it's delivering some cells and some biological elements inside. So you have simply a payload that contains some biological experiment you can imagine. This is a concept that we think about quite a bit in the context of our new synthetic biology initiative here at NASA Ames. And we're really not just about delivering these biological elements in containers that stay isolated, but we're really all about thinking that synthetic biology and biological cells might interact with the environment. So we're talking about getting rid of the structure that contains them and just having them interact on the lunar surface. So our concept of organic molecules on the moon, therefore, is expanded. Of course, meteorite impacts and interstellar lunar dust provide a background spectrum of molecules, but human-delivered organic molecules in the future, I think, are going to be very important, and that sort of expands the range of concepts that we need to think about. We're talking about not just microorganisms, of course, although that's a primary focus. We're also talking about man-made organic molecules as well. So if one thinks about taking organic molecules to the surface of the moon, one has to contend with the very harsh environment of the moon from the standpoint of the radiation environment, obviously the very deep vacuum that's present on the moon. There is full spectrum UV light, of course, which is a very important aspect of this environment. Solar wind protons, protons in the 1 kiloelectron volt per nucleon range are abundant and probably have an effect on the chemistry of organic molecules. Galactic cosmic rays are much less abundant, but more highly energetic, and many space scientists are beginning to think how these types of radiation may interact with organic molecules. And of course, my favorite, solar particle event protons, highly energetic and at times, at episodic events, very abundant as well. So these are all of the radiation sources that could affect organic molecules, but we're really interested in not thinking about so much the direct radiation effects, but one can think about these as the indirect radiation effects. So with these as the many of the molecules of interest, the polycyclic aromatic hydrocarbons as being a major substrate for these types of radiation effects. We're also talking about the potential for these same radiation sources to now induce a chemical reactivity in the lunar dust or the lunar regolith, and then to have, in essence, indirect effects of the radiation on these organic molecules. So we think of radiation-induced chemical reactivity of the regolith as an indirect radiation challenge to the full spectrum of organic molecules on the moon. So that's the point of view that we're coming from. Well, we've spent a lot of time studying the chemical reactivity of lunar regolith, and to be honest, we're just beginning to get a handle on what many of these radiation effects can do to the lunar dust and the heavier fractions of what's on the moon. The focus is on chemical changes associated with SiO2. That's certainly of significance because about 50% of lunar regolith is in fact SiO2. The Si radical and SiO radicals are probably formed as a result of homolytic bond breakage as a result of all of these radiation processes, including UV light. All of these processes are energetic enough to cause bond breakage. So one can expect that free radical chemistry is going to dominate the types of reactions that organic molecules will participate in terms of interaction with these minerals. The problem becomes more complex and arguably more interesting when oxygen and water interact with lunar regolith and form hydrogen peroxide and hydroxyl radicals. And certainly in regions of the moon, in polar regions where water or water ice is present, these reactions can take place. And lastly, the presence of nanophase iron probably adds a level of complexity and interest, surely, that may make it a little bit hard to interpret some of the studies that are done in the future, but certainly enhancing production of hydroxyl radicals by Fenton-type chemistry is something that's certainly been seen. So as I think about the problem, obviously much of our thought, much of our speculation is about aromatics, benzene molecules, polycyclic aromatic hydrocarbons, and it's worthwhile to think about this first in the absence of water, and certainly the silica radicals that are formed by homolytic bond breakage can cause direct interaction with aromatic compounds, forming aryl radicals, which can then go on to form biphenyl groups, which should be detectable spectroscopically. Silyl ethers can form from SiO radicals as well, and certainly those types of molecules have unique spectral signatures that we can examine as well. The more interesting reactions from my point of view are those that take place when these potential reactants interact with regolith that exists in water or has been exposed to water, so that many of the aqueous free radicals become the primary reactants. So we're thinking about, for instance, hydrogen peroxide interaction with these aryl groups to form phenol groups, again with easily detectable spectral signatures. Hydroxyl radicals can participate in similar sorts of chemical reactions. And then superoxide anion, probably not the most abundant species in ecosystems, but an important one can participate in a variety of aryl oxidation reactions depending on conditions. We've used a number of techniques to study these processes, really focusing on how do you generate a reactive mineral species. And we really want to consider all of the different methods we've been using. UV light from various sources, proton exposure, and even mechanical grinding of regolith is a very effective way to generate reactive surfaces. And of course, we use a variety of spectroscopic tools, EPR and FTIR, to analyze the products. So I just want to acknowledge my collaborators and thank you very much for your attention.
Thank you, David. Are there any questions in the audience? Oh. Someone that's not Mike Wargo will let him ask a question.
Have you thought about accessing the fresh bags from the Apollo missions?
We've thought about it, but those are so distant remotely that so many subsequent reactions could have taken place. I think it would be a challenge to do that analysis, and in the end you wouldn't be sure about the results. So we've only given it a passing thought.
Okay.
Thank you.
Anything else?